right, so we've got a kid on a slide. A kid on a slide. And so I want to draw myself a slide. Oopsie. I'm going to draw myself a slide. And my little kid sitting there. And my slide has a height of 10 meters. I'm going to say that along the length of the slidey part of the slide, what do you call the slidey part of the slide? The slanty part? You know, the slide. Along this part of the slide, at any rate, regardless of what the technical name is, along this part of the slide, we're going to say that it's 15.6 meters long. And since this is a slide and this is the height, we're going to understand that that's a right angle there, okay? It's 15.6 meters. Now this kid's going to go down the slide, and I got a few questions I want to ask about this kid. Find the kid's EG, gravitational potential energy, at the top. Assuming a kid going down a slide starts from rest. That doesn't affect the EG, but I'll just tell you the kid's starting from rest. What's the kid's EG at the top? Somebody said, oh, he didn't give us a mass. Let's give the kid a mass. 10 kilogram kid. Nice round numbers. It's a little person. Okay. Okay, so 10 kilograms times 9.81 meters per second squared times 10 meters, dropping off my trailing zeros to keep my notation small here. Well, 10 times 10 is 100. 100 times 9.81 is 981 kilogram meter squared per second squared, or joules. 981 joules. So the next question I want to ask is the kid's total kinetic energy at the bottom if this slide were frictionless. Okay? You don't have to look very far to figure out what the EK is going to be at the bottom. You could say that E total is equal to EG plus EK. What's EG equal to at the bottom? Zero. So I know Chris already had his hand up. What's EK at the bottom, Chris? Beauty. So E total didn't change, and at the beginning, E total was all wrapped up in EG, so now EK is equal to 981 joules. All right, now I gotta let you in on a secret, because as this person is sliding, there actually is friction. Okay? Because it's the real world. Friction's working against your motion. And this kid has a kinetic friction acting on him of 100 newtons. All those digits being significant. So 3 significant digits, 100 newtons. We could say 1.00 times 10 to the power of 2, but I'm just going to write it as 100 newtons. Kinetic friction is 100 newtons. So question C, how much work is done by friction on the kid? That is, how much work is done by friction on the kid as the kid slides down this entire slide? So the work formula is work equals force times displacement times cosine of theta. Now the force that we're talking about here, because we're talking about the work done by friction, we can throw that into the subscripts. The friction force and the displacement are going to be in opposite directions to each other, right? Because the displacement is going to be down the ramp, and the friction is going to be acting up the ramp. So we could say that, oh no, we changed it. We said, oh, we said, find the kid's total kinetic energy for a frictionless slide, and then we said, oh, wait a minute, this is the real world. Let's bring it back again to reality, okay? So the friction we said is 100 newtons. Okay? So throwing in that 100 newtons for friction, as the kid slides along, what's the displacement that I'm going to use? Is it the vertical displacement or is it the angled displacement? Angled, yeah. 15.6 meters. That's a pretty big slide. It's like one of those amusement park slides, I guess. What's the angle between displacement and the friction force? 180. Well, remember with work we don't assign positive and negative values. The cosine of the angle assigns that for us. So cosine of 180 degrees becomes the -1 for us. Okay? So negative 100 times 15.6 is going to be
1,560.
beauty.
Meaning he can't slide down the slide.
Yeah. Is that right?
Yeah.
Dang it! Can this kid can't slide down this slide? Why not?
The friction is too great.
Shoot. He can't get all the way down this slide. Oh my gosh, that stinks.
Well, too bad.
What if we greased up the slide a little bit? Let's grease up the slide just a little bit. You know, you have a little bit of fun at the playground. Put a little bit of Vaseline on the slides and see if the kids just like keep on going. Right? Don't do that. That's not very nice. Let's say that we go back to the playground and we say, kid, you didn't make it down. Have you ever been on one of those slides before? I can remember, Brant Hills. I was sitting on a slide when I was a little kid and I got stuck. You know, your little thighs, you get stuck and you get like a little slide burn. Oh, dang. Okay, so let's say we go back and we grease up that slide. What do you want to grease it up to have a static or kinetic friction of? 0. No, that's ridiculous. let's make it be half, okay? Let's say that we get it nice and slippery. We get it down to being 50 newtons. And we say how much work is done by friction on the kid if, let's try and word this carefully, if we grease up the slide. If we grease the slide. Okay?
780.
Oh, you beat me to it. Okay. So work is equal to Fk, same formula, times delta D, times cosine of theta. We plug in our values. I halved the friction force, so you actually do end up halving the work as well. 780 joules of work.
Yeah.
Okay.
Still can't go down the slide.
Yeah, you
Why can't you go down the slide now?
I don't know.
You got gravitational potential energy to give up? That's how much work friction's going to do us? Yeah, we'll make it down the slide this time.
Yeah.
So that kind of jumps ahead to the next question, I suppose. The next question is, at the bottom, oh, we can see that he's going to make it. He got more energy than the friction's going to steal from us. How much, kinetic energy does the kid have at the bottom? How can you get that?
This one still has 981.
At the bottom? Well, that was if it was a frictionless slide.
But that's kinetic, it's not as total.
I'll say it again. Up here, his total energy was equal to Eg plus Ek. And what we're saying is down here, initially we had a frictionless slide. It was a perfect slide. Eg plus Ek. And the only thing that had given, or there had been nothing to take away energy from this system. And so the Eg up here was the total.
Okay.
And down here, before we greased the slide, when it was a frictionless slide, before we introduced reality a little bit here, we said that Ek was going to be exactly equal to the original Eg. And now what we're saying is that E total is equal to Eg plus Ek plus the work that's been done on this kid, essentially, right? And now the work that's been done on the kid is a negative value, so the kinetic energy is going to be a little bit less now.
The total energy is equal. That stays the same, isn't it?
No, the kinetic energy does not stay the same. You're actually reducing the amount of energy that's getting done on this kid. Okay. Oh, sorry, the total gets less. You're right. Total gets less. No, the kinetic doesn't stay the same. The work took away from the total energy. Okay? So we got a total energy of 981 joules before. We took away this much energy due to friction. Is that understandable?
Yeah.
And that leaves us with a new kinetic energy. Okay. So E kinetic, now that there is friction, is going to be equal to the total energy that we started with minus the work that was done on this person. Or I suppose we could say plus the work, but the work is actually a negative value. Okay? So we'd say 981 joules minus 780 joules,
201.
201. 201 joules. Pardon me? We can just say that it's E final. It is just kinetic energy.
Can you just say over there that ET minus W instead of ET plus W?
Yeah, the ET plus.
You can say ET plus W, but the W is a negative value, so
Yeah,
you're right. Yeah. Yeah. Okay, so 201 joules. Now, if we know that there's 201 joules of kinetic energy with this greased up slide in a real frictional world, can we figure out how fast the thing's going? Yeah, so 1/2 mv squared. We can do that calculation. That's very doable.